Hey there, in this lecture, I want to describe two fundamental concepts in the pi space theory. Um, they're two fundamental things in reality, and I just want to explain how to describe them. The first thing is velocity, and we it's just how we measure the speed at which we move from one place to another. The way we do it is we measure distance and we measure time, and then we say speed is distance over time, and then we come up with velocity. Then there's this other idea in our world. It's the concept of gravity, and there's concept of energy. So all of those very kind of highbrow ideas. Energy is a kind of a highbrow idea in that it's kind of everybody knows what energy is, but they don't really know where it comes from. We have the famous Einstein equation, E is equal to mc squared, and even when Einstein derived it, he wasn't quite sure what it meant. In pi space, it's really easy. So let me just describe how to describe velocity and gravity and energy in pi space. And this isn't so much a mathematical treatise as a description of the theory itself, really simply. So in pi space, we focus at the unit of interest is the atom, and clusters of those atoms can form larger pi shells, or a single atom can be a single pi shell, or a larger collection of them, like in a planet, can be also a single pi shell, but it contains lots of smaller atoms. So in the diagram I show here, we have an atom or a pi shell which can go from 0 to the speed of light. All that velocity is in the pi space theory is compression of an atom. It gets smaller. Diameter gets smaller. So what we do is we have a notation that shows what's called the diameter line. So the diameter line represents velocity. So you might say, what does velocity, how do you represent velocity in the pi space theory? I say it's the diameter line of a pi shell. And you might say, what is a diameter line? The diameter line represents the diameter change in the atom or the pi shell relative to a stationary observer. And that's it. It's really simple. There's some maths here which I won't go into, but that's the basic idea. Really simple. You just represent it that way. So the unit of velocity is the diameter line divided by c, and c just represents the total diameter of the atom. Okay, so that's velocity, right? It's a sphere or a circle with a diameter line, and the proportion of the diameter represents velocity. That's all that it is. So you could have a smaller pi shell, and 25% of that would be smaller than 25% of the other pi shell, and then you get into relativity. But the point is, if just in real simple terms, it's a sphere represented as a circle here, and the velocity is the diameter line. That's it. That's all you need to know. Right? Now, gravity, right, and energy. Let's go on to the idea of gravity, right? The famous equation that Newton came up with was this one here, which is the force of gravity is g times the mass of the two bodies divided by r squared. The fully qualified version of that formula in pi space is there's a pi here. It's pi r squared, where r represents the diameter. It's like a large pi shell. But let's just ignore that for the moment. The point is, let's just stick with the Newtonian viewpoint. That's fine. So that's the formula. That's the force of gravity, right? Now, what is gravity in pi space, right? Okay. What gravity is in pi space is really simple. It's basically atoms or pi shells uh, changing their area, right? So G, the gravitation, if you figure out the force of gravity, right, what you're actually doing is you're figuring out the area change of the sphere with respect to distance, right? Okay, that's all you're doing. So, so when the very first experiments were done on gravity by Galileo, what he did was he rolled objects down inclines and he said it's this distance and it took this amount of time, and he measured distance s and he measured time t. So what he discovered was s was proportional to t squared. It's kind of been lost over the years, this s is proportional to t squared, but if you go all the way back to the original research done on gravity, the very first thing discovered was distance s is proportional to t squared, and they never really solved why that was. So in pi space, you might say, why does it work out like that? It's really simple, really simple. The atom. So when the original research was done on gravity, s was found to be proportional to t squared. Now time t, every pi shell has a clock tick, and they all run. If the pi shells are the same size, their clock tick runs at the same speed. All that the time t means is that it's the event processing rate of the pi shell or the atom. Now, what I'm showing in the diagram is s is proportional to t squared. So s represents the distance that an object travels in under gravity. If you fall under gravity, right, what's happening in pi space is your atom is getting smaller with respect to the distance that you're falling. So the atom is losing area at a constant rate with respect to distance, right? And the distance it travels is proportional to the gravitational constant. So it's s is proportional to t squared. So the area loss is constant as you move down, and you can see that in the formula that is derived, which is the kinetic energy equals to the potential energy. So the half mv squared is the sum of all the areas that you would lose, and then you can put that equal to g times h. And g is actually an area change in the of the atom, and if you want to be more precise about it, it's g divided by c squared, right, which is this energy idea. And all that means is that the c squared, that means it's the total area of the sphere. It's actually the fully qualified version would be g divided by pi times c squared, but just for the purposes of keeping with the Newtonian idea, it's g, or the Einstein idea, it's g divided by c squared, and that is the proportion of the atom losing area. T squared is the reason why s is proportional to t squared is that the time is proportional to the diameter line. And if you want to if you want to map from a diameter line to an area, it's pi times d squared, which is what's called the square rule. So, and that's why it works. If you want to get the area of this atom, what you do is you use what's called the square rule, and that's just the area of a sphere represented in terms of its diameter, pi times d squared, and the full diameter, therefore the d turns into c, so it's pi times c squared. And this is why E is equal to mc squared. right? The energy is a combination of the mass and the area. So energy equals the mass inside the sphere times the all the area of the sphere, which is pi times d squared, and d is the total compression is c, so it's pi times c squared. That's the fully qualified formula in pi space. So basically, in the Einstein work, you just drop the pi, so it's E is equal to mc squared. So I'm talking about everything here in terms of pi space, but the formulas, I'm just trying to explain how the formulas map to pi space, and this is so that's what gravity is. So the gravity field changes the size of the atom, and then the atom is what produces the force. That's it.